In the last unit we observed that once you come up with the loop invariant, you're home free. And we also showed you some tricks on how to come up with loop invariants. So in this unit, let's go through the motions of deriving some of the other parts of the loop. We will derive the loop guard and we will derive the initialization step. In order to figure out what the loop guard should be, you need the loop invariant and you need the post condition, and you focus on that. So let's look at a concrete example. Here's the concrete example that we've used before, where y gets updated by adding the entries of x to it. And in this particular case, we picked the loop invariant such that the first part of the array has been left alone and the second part has already been updated, which means that we are inherently marching through the vectors from last element to first element. So let's focus on how to come up with the loop guard. And the necessary information is highlighted here in the blue boxes. Here we just focus on that. And notice that the purpose of the game is to come up with this loop guard G. Now, we know that the loop invariant, together with the fact that the loop guard is false, must imply the post condition. Now, if you look at this, if k were forced to be equal to 0, then the orange box would be a quantification over the empty range, so that would evaluate to true, and then the rest of it would just be a quantification over the entire range with 0 less than or equal to I less than n. So that's exactly the post condition that we're after. So we want to pick our loop guard in such a way that 0 less than or equal to k less than or equal to n, together with the fact that the loop guard is no longer true, implies that k is equal to n. And the choice is obvious. If we pick the loop guard to be 0 less than n, then not 0 less than n together with 0 less than or equal to k less than or equal to n forces k to be 0, and we're home free. And then once we know what the loop guard is, we can fill it in the various places where it needs to be in the worksheet. Okay, next we turn our attention to how to derive or develop the initialization command s sub I. For that we look at the precondition and the loop invariant. Let's focus on that and let's annotate it a little bit. If we look at this, if we pick k cleverly, then the precondition and the loop invariant are one and the same thing. Namely, if we pick k to be n, then what's in the orange box in the loop invariant is exactly what's in the precondition, and what's in the yellow box is a quantification over the empty range, which then becomes true and disappears. So, the obvious solution is k is equal to n, but we actually can also do so formally. We say, what should k be? Let's assign it some expression e. Let's plug that in. And then let's ask the question, does the precondition imply this weakest precondition of Si leaving you in a state where the loop invariant is true? And if you look at that, you come to the conclusion that the expression should be chosen to be n, and then we know that n should be assigned to our variable k. And then we can plug that into our worksheet. And now all we need to do is to develop the loop body itself, the command s that is in the loop body. And that we will look at in the next unit. So in summary, given a precondition and a postcondition, we can systematically derive loop invariants. Given the loop invariant and the postcondition, we can systematically derive the loop guard. Given the precondition and the loop invariant, we can systematically derive the initialization command.